Good morning. There's usually a cheat sheet here with the speaker's biography, and there isn't, so I'll have to make it up. Carl Heltzel, Ph.D., organic chemist, formerly on the faculty of University of Kentucky? Some Kentucky university down the road from the university. Came to us on the recommendation of Boyd Haley. He's kind of a Boyd Haley protege, and he has been functioning paid just about what I'm paid for the job as our science director for the last year and a half, and has provided a lot of information, a lot of insight, a lot of grunt work in the laboratory. He's reporting this morning on Bisphenol A leaching from dental composites. It's a pilot that funded entirely by IAOMT and performed entirely by Dr. Heltzel. And our way of beginning to take responsibility for what we think is the more biocompatible approach to doing restorative dentistry. Let me introduce Dr. Heltzel.
Oh, hello. Good morning. Okay, so I changed the title slightly this morning. I stopped in at the University of Mississippi to pick up my bioassay data, but it's not ready yet. So the endocrine disrupting activity of the composites will be uploaded on the web page, and I'll just continuously update the data as we take in more samples, more composites, flowable sealants, and so on, test them. We've developed just a protocol now where we can just shove it through, and I'll keep uploading the information. Yeah, it's not really, it's the good news and the bad news. I've got some information, but I'm not sure exactly what the conclusion is going to be, right? There's a lot of confusion still, and a lot of arguments over endocrine disrupting activity and at low doses. So let me just jump into this and I don't know, I thought I would start with a joke of some sort. And this is sort of hopeful and wishful thinking, maybe. But here's Obama bringing the scientists out of the cave and, as he said, restoring them to their rightful position. And we hope that's true. Right? I think that we're going to see some changes. And hope for the best. But the talk is on bisphenol A. There's the chem abstracts number. I have a pointer pen here. Here's a three-dimensional model and a little duck. But there's a three-dimensional model. It shows you that bisphenol A is not a flat molecule. Rather, those benzene rings are twisted slightly in order to give them room to stay away from each other. It's a high production chemical, okay? 4 billion kilograms in 2006 on a global scale. In 2007, just in the US alone, over 1 billion kilograms of the materials been produced, okay? It's not a naturally occurring product, okay? This has not been found as naturally occurring. So it's what's in the environment that we put there. It can be found in drinking water, surface water, sediments, groundwater, soil, as well in industrial waste treatment products, and of course, us. And on the wastewater, I don't know why my clicker is giving me grief.
Point the clicker to the computer.
I'm trying. So contact with drinking water occurs primarily through polycarbonate for water pipes, resins used for coating cans, the polycarbonates in water bottles and so on. But here's another thing about, it's ubiquitous, huh? The polycarbonates and the bisphenol A has been used in the manufacture of compact discs, glazing application films, food containers, medical devices, including the sealants, flowable composites, injected molded parts like alarms, mobile phone housings, coil codes, displays, computer parts, and on and on and on. And I intentionally ran it off the page. But the idea is that we're surrounded by it. And there's no getting away from that fact. It is a big part of our lives. I must not have the touch here. I'm pointing at the computer. We've got some information on exposure rates. So if we want to talk about risk, we're going to need to talk about exposure and toxicity. There was a large, not very well. What number are you hitting there? Yeah. Is that back and forth? Okay. So it's a rather large scale study of adult populations, urine analysis, showing mean daily intake of somewhere between 4 and 5 micrograms a day for adults of BPA. It rapidly decomposes. And so that suggests that it's a continuous exposure. And continuous, and it's all around us. This is just to give you a little idea of the polycarbonate market. Medical accounted for about 9% of that. And then we're exposed to it, of course, through all these other uses. Why would I choose to do this study? I was asked to. And as soon as I looked into it, I thought, this is something to be concerned about. And it's something that I might be able to have a hand in and helping out. I had heard that and looked into it and saw at that time, which was about a year ago, there hadn't been a whole lot of human studies done. But the CDC had a sample population, about 25 people, and found that 93% have traces of BPA in their urine. Not surprising. Another reason to do the study, we've got a lot of misconceptions out there, a lot of data coming from different parties that are conflicting reports. A year ago in New Orleans, Professor McLaughlin from Tulane was there, and he presented the data. And he had mentioned how NIH had commissioned 2 different studies, and they got 2 different results. One study was made up mostly of industry types, and the other study was more of an academics, higher number of academics. And that study said there was a reason for concern. When the study done by the industrial folks, they said no need to worry. Let's continue to do business as usual. And so I've got some references as we go along, some at the end. I'd be happy to provide you with a complete list of them. And the IAOMT website is an excellent place to start if you want to look into BPA. I promised Dr. Gregg that I would include some organic chemistry, and so I was just going to just give us a little primer here on, say, a very simple polymer made up of monomer of BPA, and all you got to do is take some base, like sodium hydroxide. Doesn't even have to be that strong of a base. Pull off those protons. Right, so you got a dianion, react that with some phosgene, and you'll get this phosgene ester, or really it's a carbamate type ester. And again, it'll do it again on the other side. And organic chemists always like to draw arrows and show how electrons are moving and bonds are forming. And so I just sort of repeated it again here and showed, here's one very simple BPA containing polymer. Okay, so now the composite resins, which my mouth is full of them now that all the mercury's been removed. They are commonly based on bisphenol glycetylmethylacrylate, or Bisphenol A. And I've given us a structure here. Now, if you were going to take your arrows and try to show a mechanism for breaking this bond here and freeing up the BPA, it's complicated. It's not as straightforward as what I've just shown. And I'm not going to bore you with those total details, but your dimethylacrylate area here, this is your ester bond linkage. This is what's susceptible to attack by water and acid. It could be acid catalyzed or base catalyzed. In addition to the Bis-GMA, there's Bis-DMA. Probably not used too often anymore because this is quite easily hydrolyzed to free up BPA. And in addition to the monomers and fillers, because I don't want to give you a whole lecture on polymers, but you know what a monomer is and a polymer is, right? 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 Okay, good, thanks. And, but there are many other things in the proprietary blends of composites, and those details are not readily accessible. And I was up again late last night, still searching and looking at MSDSs, and it's hard to tell what's in some of these. You know, they give you quite a large window of allowance of saying what's in there, what's not. And of course, everybody writes their own MSDS. There's no standardized format. So these extra stabilizers, initiators, that is, if the polymerization is a free radical mechanism, you've got to have some sort of a free radical initiator. These are also materials that are really not, they haven't been tested for toxicity either. therein lies the problem. We've got a bunch of chemists out there in the world putting out somewhere on the order of 10,000 chemicals a year, new things, putting them in the environment. Yet very few of us have ever had a toxicology course. On the National Committee for the Improvement of the Environment for the ACS, and nobody in the room had a toxicology course. And I find that really amazing, that we're producing all these chemicals, we're putting them into products, but yet we haven't tested their toxicity. Yes, and so the common misconception, which I think for this group at least, probably already understands, there's no free BPA in the composites. Right? The BPA is a result pretty much of hydrolysis of some sort of a polymer or uncured polymer. And so you've got residual BPA possibly that can also be available to leach out. Any questions? How about a question?
Yeah, I still don't understand the relationship between BPA and GMA.
BPA and bis-GMA? Yeah, as I said, it's not so readily. I could show you the mechanism, a proposed mechanism for freeing the BPA from bis-GMA, but it's a matter of hydrolyzing the ester bond. A couple of things happen in this region before you finally free up the BPA. It's not as straightforward as this one. Yes, sir.
So it's not easily released, you could say, from the polymer, but there is free BPA floating around in the composite.
There could be, yeah, if it's not cured properly, or not thoroughly.
So they can be cured properly, but they may not be fully cured.
That's what I mean. Well, I guess that's a better way of putting it. Have I answered the question over here? Question in the back.
Your statement at the bottom said there's no use of free BPA. Is that the same as saying there is no BPA that gets out of the composites?
Now, what I'm trying to say here is that the developers of the composites are saying that they don't put free bisphenol A in a product in the capsule on purpose. It's all in a polymerized form. And then when you cure it, they cross-link, they tighten up. You know, the BPA is added to give it some flexibility and some give. But there's, you know, when you're handed a capsule of it, there shouldn't be any free BPA just floating around in it. It should all be incorporated into the polymer itself, whichever one it is they use.
Second, please.
If we hold all the questions to the forum speaker tonight, some of the questions may be answered during the presentation, and this evening we'll have a mic so everyone can answer the question, please. So hold your questions. If there's any time after the presentation, perhaps Carl can answer them, okay?
I'd be happy
Thank
to.
you.
I apologize for starting a riot. Let's see. I don't want to try to give a complete timeline and history of the use of BPA, but just a couple of highlights. You know, McLaughlin's work was started in the 70s, but not until somewhere around 96 was it become public awareness of it, and or scientific awareness, and then leached over into the general public. And that was the Granada group and those at Tufts. Of course, it's not a very large sample group, 18 men and women. They collected saliva samples 1 hour prior to and after the application. and found somewhere on the amount, on the order of 3 to 30 parts per million of BPA in the saliva. That report has been attacked and discussed and reviewed ad nauseum. And what OAS said was that the BPA leaches from dental sealants in composites. It's likely to be from hydrolysis of Bis-DMA, as well as uncured, not totally cured polymer. There's the reference. Well, I just have to show some more organic chemistry. And so here's the link, I say, and subject to hydrolysis. All you need is a little bit of acid, a little bit of base, a little bit of water, and you will just chop this right off, giving you bisphenol A and this dimethyl acrylate carboxylic acid, depending on whether it was an acid or base. You'd have the acid form or the carboxylate, along with all the other things that are in the composites that we're not exactly told what they are. 2002, there was a study by Polgar where he started looking at specific brands, and they found leaching of BPA, also Bis-DMA, Bisphenol A as a diglycyl ether, Bis-GMA, some ethyl and propyl esters of bisphenol A, and they had, for the first time, used controlled pH and temperature conditions. So what you're seeing is a lot of different things come out. And in this study, I was asked to sort of just rank or take a look at the amount of BPA. So I've narrowed the sweep of my GC tracings to just that region. You could also go back, and I have full sweeps, and try to identify all the other peaks, but that wasn't my charge at the moment, so that still could be done. But, let's see, so Polgar says the amount that's leaching is similar to those, and I need a space there, that have produced biologic effects and in vivo experimental models. I'm not going to go into all that. That's out of my field. Here's the Bis-GMA. Now we're up to 2004. By 2004, we've got over 115 published studies showing these effects of low doses of BPA in experimental life forms. And I'm sure you're all familiar with the idea that emerged that low dose doesn't follow what we were trained to believe, which is the dose makes the poison, and higher dose means higher effect. That's not true in endocrine disruptors. At low doses, we can see a greater effect than in higher doses. And people are still arguing about some of this. All the way up to 2008, the NTP finalized their report with this statement, current human exposure to BPA is of some concern for effects on the development of prostate gland, brain, behavioral effects, especially in children, developing fetus. They put that in this five-point scale. They sort of just put it there in the middle. Well, we've got some concern. The controversy continues. In 2008, you see, I was going to list a number of other ones, but this would do for now. But there's a number of reviews out there that are still trying to make sense out of it all. Now, the study that we did, in order to quantitate the amount of BPA that comes out of the composites, we first made a calibration curve using known concentrations from, I think, 100 parts per billion down to 1 part per billion. And you can see a nice linear curve. And that allows us to then take an unknown quantity, use this curve, and come up with the concentration of BPA that leaches out. Oh, boy. Let's see. Can you see this? All right. Here's your BPA, and this is its mass spectrum. Okay. The molecular ion, that is its molecular weight here, is not very big. It's because one of the methyl groups pops right off as soon as it gets into the mass spec. Puts a positive charge on that carbon. It's highly stabilized, and that is what this peak here is. It's the most abundant peak, the most stable fragment in the mass spectrometer. Now, BPA alone, put through a GC, this is the GC portion here, the chromatograph tracing, and you'll see that it's got this tailing. It's just not ideal for trying to integrate the area under the peak. So, according to a couple other studies, decided to go with a trimethylsilyl ether derivative. And that gives us a nice, beautifully shaped peak. It comes out in a reasonable amount of time. And that's how it was done. I could show you the mass spec of that. Again, the molecular weight, or the molecular ion, is 372. Take away 15 for one of those methyl groups, and there's your base peak, your most abundant peak. That's what you would expect to see for this molecule. We took painstaking efforts to reduce the BPA in the project because it's everywhere. You buy a box of vials, well, they come in a plastic bag. You buy containers of chemicals, they come in plastic containers. You know, so we had to go back and repurchase chemicals to make buffer solutions, and glass containers, triply distilled water in glass containers, never been in contact with plastic, and everything else we could think of. Of course, we have an auto-injector, and it still goes through a tiny little rubber septa, which we couldn't get the composition from the manufacturer. What this slide here shows is that I took the matrix, that is the buffer, the derivatizing agent, the BSTFA, pyridine, which is the base we used to help derivatize it, spiked it with 50 parts per billion BPA, and got back 49.72. It's a 99.4% recovery, and this is an indication of the validity in the statistics. You know, so we have a lot of more data like this, where I've tested and looked at each individual component alone, each reagent, each buffer, and so on. In fact, here's a buffer at 5.81 showing no BPA, which we were thankful for because the first go around we were just not able to get it down to zero. It was impossible. In fact, it's the zero is not really zero. It's somewhere around 0.1. 0.01 parts per billion, something like that, but it's effectively zero. The initial results I had run at first, there was some concern about removing that oxidative layer by polishing. So I took some diamond light and ran it, polished and unpolished. And as you can see, the precision was awesome. But it also told us that we didn't need to polish all the samples because it wasn't going to make any difference. so the rest of the samples were run unpolished. I tested everything, the pipettes. There's a little piece of plastic at the bottom of the box. Tested that to see if that could be contributing to anything. Used as another control a polymer that I got from the University of Kentucky material science people that has no BPA in it whatsoever. Ran that through the same protocol and saw no indication of BPA as another control. And here's, I guess, what we've all been waiting for. I've got 12 samples here, all done in duplicate, all done at 2 pHs, and this is after 24 hours. Initially, I did 1 hour and then 24 hours. Second time around, I just took one sample out at 24 hours, evaporated the buffer solution, took it back up in our derivatizing agent, the pyridine, and injected that. These are now sitting in another milliliter of buffer, and at 30 days, I'm going to take another look and see. I haven't seen studies that take the data out that far. When we did 1 hour and 24 hours, there was very little difference, and so we were seeing about the same amount of BPA leaching out every day. So we'll see what happens after 30 days. Diamond light seems to leach very small amounts of BPA. 6.74 parts per billion per plug. That's somewhere on the order of 1 times 10 to the minus 3 nanograms per milligram of composite material. Nanogram is a millionth, billionth of a gram. So these numbers are effectively zero until you talk to the low dose proponents but again, that data is still hard to interpret and not conclusive. But from a table like this, you can go, and I'm not a dentist, so I've never worked with composites, of course, so I can't advise you on which ones hold up well or anything. But I can only tell you that some leach less BPA than others. Some you're going to want to stay away from, especially this one, which seems to disintegrate in the buffer, even at pH of 7. I've got a picture of that. It's bizarre.
Which one is that?
That was the Virtuoso, wasn't it? Yeah, Virtuoso. So here was the deal. I had these glass sleeves specially made up so that they had an inner diameter and a height of 2 millimeters that when popped out of that glass sleeve, the plug was 1 square centimeter surface area. So they all have the same surface area. In the second study, I also weighed the mass of each one so that I could take a look at it and put it on that other scale of, say, nanograms of BPA leached out per milligram of composite. And we can put that data also on the website. And here's an assistant there curing the samples. As I guess you know, here's John May at the lab. He's doing something, I don't know what he's doing. And then here is how we would be evaporating the different solvents down to dryness using nitrogen, ultra pure nitrogen to evaporate samples. And I just love pictures, so let's see. Here's me putting them in the sonicator. There was nobody willing to give me to give up a grinding simulator. I tried, and once they heard who I was and what I wanted to do, they had no interest in loaning a grinding instrument. And I tried some different abrasion techniques, including garnet chips and agitation. And eventually, we just settled in on just keeping it sonicated at 37 degrees C. Does that simulate chewing? Not really, but that's the best I could come up with at the time. If I could buy a $50,000 grinding instrument one day. Here we've got this virtuoso. Look at this. Here's a plug sitting in a buffer solution, and it's fairly clear. But the virtuoso overnight just seemed to almost, well, it was very turbid, as if it was dissolving. I don't know if you've had anybody work with virtuoso. I would hate to just find my composites dissolving, and what we have here is a GC mass spec. This is actually a GC mass spec. It's run through twice, and so you can really work to get the limits of detection down. There's an auto sampler, so we could set it up and run the samples overnight. And this is probably no news to you, but I thought I'd go ahead and give it. Let's see, what time? What time is this over?
20 minutes. 20 more minutes.
20 more minutes. Then let's see. What's an endocrine disruptor, huh? Or xenoestrogen? And I didn't really need to probably explain to you what those are. This group of chemicals that mimic estrogen. And I had a picture of that I had from one of my textbooks of the old cell and receptor site. I think, but I took that out. I thought that I might insult somebody by that being too general. I've got a highly intelligent audience here that knows science, or they wouldn't be here. What's interesting about and here we just some endocrine disrupting compounds, and you got your biphenolics, and that's just the benzene ring with an OH on it, two of them. What's interesting is that the compounds that show endocrine disrupting activity or mimic estrogen range from ketone, this crazy looking thing with chlorines coming out all over the place. That's an adamantane type structure with chlorines popped out everywhere, to a basic steroid structure like that. It's practically impossible, as in cancer research, which is what my Ph.D. was in. You can't just sit down and devise and draw out molecules. I think this will be good for treating cancer. It's going to be hard to predict what chemicals are going to show estrogen or xenoestrogen activity. They're also hard to detect in the water systems. You know, we're not set up to do that, so it's getting through the wastewater treatment and it's getting into our home. And we're all going to start talking with higher pitched voices. Well, you know that story, I'm sure. If we go back, just to try to go back, I just cut some of those out just to remind us of some of the in red, these are sort of the warning ones, and in the gray here, these are the ones that are leaching, very little to no BPA. Again, I'd be happy to talk to anybody about putting this into other terms, other units, as in nanograms, BPA per milligram of composite material. I had all those out and did all the calculations, and the table just looked too complicated. I thought, no, they don't want to see all that. This will give you a relative ranking, but if it's important to you to know how much is leaching out per milligram of composite, I can show you how to do that calculation, simple enough. And so the bottom line was back there at the slide, but also that there's the use of the word precautionary principle, and that we should be banning the substances that are perceived to, or all the evidence isn't in yet in terms of harm. And it seems to be gaining ground here as well as in Europe. Here's a polycarbonate water bottle, just to sort of give you an idea. This, after a 3-day period, some water in a bottle like that leached over 70 parts per billion of BPA. And so what is the bottom line? The bottom line is that you're going to get a lot more BPA from your water bottle sitting in your car, especially if it's warm, than you will from a dental composite of any of those types. It's already in us. It's all around us. I think it would be it wouldn't be prudent to stop using composites because of the small amount that's leaching out. But then we can sit down with the biochemists and talk about and the epidemiologists about the low dose curve, and it's complicated. There isn't a straightforward answer, as in many chemistry topics. There's not always an easy answer. Some people will say, look for this recycling number on the bottom of your container. It doesn't always mean that there's BPA in it, but if there is BPA in it, it'll have that designation of 7. And you'll find that on the bottom of these cups here, supposedly. I don't have $5 to buy a cup of coffee, but if I did, I'd go and check one of those. What we want to do at this point now is, I polled the academy. What composites do you think we should run? And we got back a lot of information, a lot of different ideas, and so on. And we're very grateful for the composites that were graciously submitted to us. And we used only the ones that were in date. But as new composites, sealants, bonds, cements come up, we've got the system is set up and ready to go. It's not going to take much time to slam those through and come up with the same numbers. We want to get the endocrine disrupting activity numbers based on at least one assay at the University of Mississippi. It's a yeast-based assay. It happened to have crashed on them somehow, and I wasn't able to pick up the information on the way down. Of course, future work includes disseminating the results in the form of a journal article and talks to maybe the American Chemical Society, American Chemical Council, and so on. And any other future work that you can come up with. Your suggestions would be appreciated. I've just got a few sources here that I use for this talk, but really, the IAOMT website is a great place to start. And once I start uploading all this onto the website, there'll be a much more extensive list of sources where to go for information. Now here I'll end, I think, and with this cartoon. And here's Socrates talking about the unexamined life not being worth living, and the Grim Reaper saying, well, the alternative may not be such a good thing either. We keep looking into things and finding out that they're toxic. We keep it's like, here's this Starbucks cup here. We have put out so many chemicals into the world without having any idea about toxicology and the modes of action and toxicology of any of those chemicals that are in the products. And there's going to be a lot more. It's just going to keep coming up. So do you want to just drink your coffee and go on? Or do you want to examine this and pay the price? Because it's going to create a lot of headaches, But I think in the end, it's going to make the world a better place and safer for our children. And I'm a strong proponent that we add to the curriculum of Ph.D. chemists, medical professionals too, toxicology classes. And I want to acknowledge that extremely grateful for the funding from the IAOMT and everybody that has been so good to us. Over at UK, I use what they call this ERDL lab. It's a training lab, and John May runs it, Tricia Coakley, and there's a friend of mine from Virginia Tech, Fola Latipo. He was the one that got me into the lab and got me the inside discount so we could keep the rate down. Audrey Cowan, Dr. Gregg, and Pari, or Parnandi, at Ohio State University for his advice. And I would like to thank you for taking the time to listen to me this morning.